We have some outstanding speakers today in this pre-lunch session, and we shall be beginning with one who is an authority on black hole seeding. Professor Priyamvada Natarajan is a joint professor in the Physics and Astronomy Department of Yale University. She is currently on a Guggenheim Fellowship as a visiting professor at the Harvard Center for Astrophysics at the Institute for Theory and Computation. Professor Natarajan has researched extensively in gravitational lensing, dark matter accretion disks, and of course, more recently, black hole seeding. She will tell us in great detail about how these huge, massive black holes at the center of our galaxies form. So without further ado, Professor Priyamvada Natarajan.
Thank you so much for that kind introduction. It's a great pleasure and privilege to be invited here to give this talk. Apparently, this is my second visit to the Institute. I do not remember the first one. I was apparently a young child when I came with my parents here. Anyway, it's a real privilege to be able to talk at the Chandra Centennial, and I seem to have made a hobby of it this year. Very, very happy that I've been able to push forward some of the scientific ideas that he made profound contributions to. And what is different about the nature of the work now is you might have gotten a sense from some of the talks yesterday, in particular Sri Kulkarni's, that there have been a lot of observational advances, incredible observational advances, particularly in the past decade or so, and this past decade since my PhD. So I did my PhD about 10 years ago. So there's been enormous progress in this field, both driven by observations, in particular observations by the Hubble Space Telescope and multi-wavelength follow-ups of accreting black holes in the universe. So for example, what is very clearly established now is the ubiquitous presence of supermassive black holes at the centers of most galaxies in the universe. So every galaxy in our universe appears to be seated in the center in its galactic nucleus with a rather massive black hole, and when I say supermassive, in excess of 1 million solar masses or so. And so one of the challenges has been to try and understand how this came to be, how these black holes actually grew to these very large masses, because we have a very good set of ideas going back, harking back to Chandra's work, where we know that the end states of some stars would lead you to black holes, but the masses of those stars are nowhere near 1 million solar masses to 1 billion solar masses. So the challenge really has been, over cosmic time, over the age of the universe, about 13.7 billion years now, to start with very small seeds that are initially in the earliest galaxies that form in the universe, and then grow them over cosmic time, and actually figure out the astrophysical processes that contribute to this growth. So what I want to do today is present some of the exciting developments in our understanding of black hole growth in the past decade or so. And the growth of black holes is going to be, much of the work now is very much in the context of the standard lambda cold dark matter of hierarchical growth of structure in the universe. So we now have a much more synergistic understanding of how the assembly and growth of galaxies, the stellar component of galaxies, is actually tied to that of the central black holes. And because we have a really successful theory, which is well supported by observations, for how galaxies grow and build, the impetus has been to integrate black hole growth into that scheme. So much of what I'm going to talk about is in the context of this standard paradigm for the growth of structure in the universe. And how structure grows in the universe is by the merger of these so-called dark matter halos. So the fundamental units in this theory are this initial dark matter density field that has small fluctuations, that gets amplified, collapses, separates out from the Hubble expansion, forms these dark matter halos into which baryons fall in, form the first stars, and presumably the first black holes also form in those parts. So I'm going to be talking very much in the context of that structure formation paradigm. And so what I want to start telling you right away is that the goal here is to build a storyline. And I'm using that word very deliberately because there are many unknowns. And the field is rapidly evolving with data, and so you can no longer make these theoretical models which can't be ratified by data. So it's a very challenging and exciting time for theorists as well. And as I said, it's the growth in observational technologies as well as computational power. And I'll show you some of the recent results of numerical work that me and my collaborators have done, which were not possible even 5 years ago. So sort of very, very new state-of-the-art stuff. So I want to give you a brief outline. Since the audience is varied, so I should ask people like Ramesh to sort of put up with a lot of introductory stuff that I'm going to. There are many experts here, including Ramesh, and I hope you'll forgive me for the sort of long introduction. So I want to start with what we know for certain about the accretion history of black holes. So accretion is the process by which black holes grow. They feed on gas, and that's accretion. And I'll point out what the observational evidence for black holes is. So there's incontrovertible evidence for the existence of astrophysical black holes. So let me show you what those pieces of evidence are that have been garnered over the past 30 years, but the evidence now is really solid, compelling, and actually quite beautiful. And so then we'll move on to the central question where I want to spend a reasonable amount of time, which is how do the first black holes form, and how they actually grow, and some of the new ideas that me and my group have been working on for the past 3 or 4 years, and then move on to how they actually pick up mass over cosmic time, and the evidence for mergers. Thank you. Evidence for mergers, as I said, merging activity is what appears to be fueling the growth of black holes. So we have to understand what physical processes about the merger are important and relevant to the growth of black holes. And then I want to really, I hopefully will have time to get to the end of this outline, which is I want to talk about observational signatures of mergers. So further tests of the model. So further tests of this paradigm. And these are tests that can be that are feasible within the next decade or so. And one of the key tests, and one of my favorite things on the wish list for science, is sort of the detection of gravitational waves from coalescing black holes. So let's hope it happens in my lifetime. It may or may not, but I'm really pushing for it. Then I want to talk a little bit about future prospects. So there are several groups around the world that have been actively working on these problems. So we have been actually quite focused. This is a list of collaborators that I would like to give credit for. We have been focused very, very sharply on working at various aspects of this problem. So much of what I will be presenting will be our group's take and our results, but these are substantiated by the work of many other people, and I will give credit as I go along. So before I push further on, I wanted to give you some basic definitions that would be useful and a little bit of jargon that will help you understand some of the quantities that I'll be talking about. So what do we really know about black hole accretion? We know that there's a critical luminosity when the radiation pressure from the gas that's inflowing into the black hole balances gravity, and that gives us a limit which is called the Eddington limit. So the Eddington limit is a luminosity limit, and it can be translated into an accretion rate limit as well. So there's an Eddington rate which corresponds to a black hole accreting at the Eddington limit. So this luminosity of accretion, notice there's a little epsilon sitting here, and that's the radiative efficiency of the accretion process. And that's a very, very important and holds key pieces of physics there. So we have some understanding, as I will show you, of how accretion proceeds in the universe, how this process actually proceeds. So to give you a rough idea of the numbers, the Eddington luminosity for a 10 to the 7 solar mass black hole is of the order of 10 to the 45 ergs per second. Okay, so it's a huge amount, it's a huge luminosity. And it appears the reason why I'm starting off with giving you an idea of the basic accretion process is that it appears that black holes do grow bulk of their mass via accretion of gas. Or by mergers. So a merger is basically when two galaxies merge, their stars merge, the stellar component merges, and the central black holes merge. But it turns out that in the early universe, much of the growth of the black hole is through accretion or accretion induced during the process of mergers. It's only in the very late universe, in the last 4 or 5 gigayears, that mergers, direct mergers, just the accumulation of mass by merging with another black hole actually increases the mass. We will get a better flavor for it as I go on and I explain what we understand. So the other interesting thing to note is that if we try to understand what the basic time scale in this problem is, you find that there's only one real key time scale here, which is the Salpeter time scale, and that's the mass doubling time scale for a black hole of any given mass. And that's of the order of 10 to the 7 years. So what is crucial here is this time, 10 to the 7 years, is very short compared to the age of the universe today, but it was comparable to the age of the universe at early times, right? So I want you to keep that in mind. So, and one could, now that we have an idea of what the Eddington luminosity is, one might want to understand what are the wavelengths in which you are likely to see this luminosity output. So this is just a quick back of the envelope calculation to give you a sense of where in the electromagnetic spectrum you are likely to see any radiation from these objects. So if you model it as a black body, say a 10 to the 8 solar mass black hole, you find that the equivalent black body temperature is of the order of 10 to the 5 Kelvin. So that automatically tells you that you expect accreting black holes to have some signatures in the UV, X-ray, and possibly in the gamma rays. And as it turns out, now accreting black holes are detected in all these wavelengths. And much of the data that I will be talking about is from all those wavelengths. So how do you build the accretion history? How do you build this accretion history or the life cycle of a black hole that is seen in the center of a galaxy today, of a massive galaxy today? So there have been two approaches that have been followed in the past. So one approach, which was pioneered by an argument made by Salton in 1982, is that you do, you globally average accreting sources across redshift. So you integrate over redshift, and you integrate the population of sources. So you take the whole population distributed in redshift, integrate it over redshift, and you calculate an accreted mass density for black holes. Of course, you know, key to this is the understanding, I should point out here, that I will be using the terms quasars and AGN interchangeably. So key to the understanding of what these objects are is the realization in 1969 by Donald Lyndon Bell, the suggestion that possibly accreting black holes are what power quasars. These are the most luminous objects in the universe, and it appears that the energetics are such that accreting black holes are the only plausible source to be powering these objects. So when I'm talking about objects, I'm talking about quasars, the distribution of quasars over cosmic time. So this, what was interesting about this approach, and till I finished my PhD about 10 odd years ago, so this was really the only sort of approach that we had, where because we were not detecting these populations out to the most distant parts of the universe, we were detecting populations that were at redshift 3 at most, and perhaps redshift 3.5 and so on. So at that point, all we had, because we would detect the brightest objects at any given epoch and not the entire luminosity function, you didn't have an idea of how many faint quasars you had, you could only do this kind of global averaging. But in the past 10 years or so, what has really changed is our senses, our ability to do a better census of the lower luminosity quasars. So the black holes that are not accreting at such oomphy rates, we've been able to characterize that population significantly better. And so in that event, because then there's a further luminosity distribution for these sources, there's a luminosity function for these sources, what we can do is now treat the accreting black holes as a population and follow them as a population. So start out with a set of initial conditions, propagate that forward in time as a population, not as an individual whole, but as a population. And we can now track this population because there is data available all the way up to redshifts of 8 or so. So I'll show you, so redshift 8 is very, very new work, and we've just submitted it to Nature. I'll show you a very nice plot from that. But it turns out that, you know, even about 5-6 years ago, there was a significant detection of a population of quasars out to redshift 6. And remember, redshift 6 for our universe is when the universe was 2 gigayears old. So it turns out we were finding extremely bright quasars, probably powered, given their luminosity, powered by supermassive black holes, like 1 billion solar masses, already in place when the universe was 2 gigayears old. And remember, we are 13.7 gigayears old now. So that was a huge challenge. And in order to, so you had to grow the hole almost 9 orders of magnitude within 2 gigayears. And you could not do it without violating the Eddington limit. So there were initial arguments that, well, maybe the Eddington limit is not a hard and fast limit. Maybe you could be super Eddington for a little while, and so on and so forth. But you know, and the idea was that, you know, in the universe, so one interesting thing about cold dark matter models is that if there's a very rare population of objects, you can quite easily accommodate them because they're extreme. There'll always be some extreme high significance peaks in the matter distribution. So if they are rare, we're good. But it turns out this is a huge population. They're turning up, you know, in very vast numbers. So you can't really say, well, these are very rare objects and get away with it. The numbers don't quite work out. So there's been a huge challenge. So that's what opened up the challenge for trying to think about new ways to make black hole seeds. Was this challenge of trying to have in place 10 to the 9 solar mass black holes, supermassive black holes in place 2 gigayears after the Big Bang. So let me then quickly start giving you a better flavor for the observational status of the field. So it turns out that the astrophysical environments of black holes, so the black hole itself, the event horizon, the Schwarzschild radius, are not that easily accessible in terms of data for a whole population, right? So what we really do know much better are the environments of these black holes that allow us to model their accretion rates and so on. So it turns out that there are 2 modes of accretion in the universe, in X-ray binaries as well, and in galactic nuclei, which is sort of what I'm going to focus on mostly. And you find that, in fact, like if you look at the center of our galaxy, the accretion rate in units of Eddington rate is really wimpy. It's 10 to the minus 7 or so. So the black hole at the center of the Milky Way, which is a few times 10 to the 6 solar masses, is actually not accreting, it's not growing, it's doing nothing. It's essentially dead. So it turns out that this is the more common kind of black hole in the universe. And the ones that are actually quasars that are very, very luminous are the rarer objects, it turns out, relatively speaking, in terms of the population. So in the local neighborhood, for example, in the neighborhood of our galaxy and in the local group, there is almost no galaxy that has a bright quasar. So locally, bright quasars are extremely rare. So most of the galaxies and galactic nuclei are sort of in this mode, where they're accreting very, very inefficiently. So I should point out here that, you know, a lot of very nice analytic work that in some sense predated the finding of large numbers of these nuclei happened with Ramesh Narayan's group at Harvard. So let me move on to some of the observations of galaxies and quasars at high redshift and at low redshift. As I said, the evidence that's been mounting for a large population, existence of a large population of accreting black holes at higher redshifts. So this, you know, you can't actually see it, but, you know, you can't even quite see it here. There's a little arrow here, and there's a little red blob, and that is actually the brightest, one of the brightest quasars in the universe. And it's at redshift of 6.8 or so when the universe was about 2 gigayears old. So there's been a real census from large surveys like the Sloan Digital Sky Survey and 2DF, where people are turning out a population of these objects. So they're actually intrinsically very, very bright objects, so they're accreting at huge rates and powered by about 1 million solar mass black holes. Closer to home, what this is a plot of the mass of a central massive object versus the B magnitude of the bulge or the inner region of a galaxy. And I think Ajit showed this yesterday, or showed a version of this plot yesterday before, where you see a correlation between these 2 quantities, and in fact the correlation gets tighter if on the x-axis you plot the velocity dispersion of the bulge instead of the luminosity. So it gets pretty tight. So what is shown here in red are points, these are from the Virgo cluster galaxy. So these are black holes in the centers of galaxies that are in a cluster, and note that they appear to be slightly offset from these black points, which are the masses of black holes, which is on this axis, as a function of velocity dispersion of the bulge for local galaxies. So I want to note here that these are all dead black holes. So none of these are actually accreting. Okay? So these are all nearby. This is from the nearby universe. This is from the distant universe. So one of the other important pieces of evidence has been, I think we may want to take some of the lights down a little bit. Can we do that? Because I think you can't see anything here. Maybe that's better. Okay. Anyway, you can't see it too well, but you've got to take my word for it. So what this is the spectrum of the X-ray background. So this is the integrated emission from all black holes in the universe at all various distances from us, and this is the X-ray flux from all those sources. Okay. So this is the spectrum, and you find that the spectrum is actually hard in terms of the spectral shape and slope, that what you require in order to understand this spectrum is a combination of two populations of sources. One that is very obscured by dust in the universe, so there's re-radiated radiation from the infrared, and then a population that is unobscured, that is very, very bright quasars, which are seen in the X-ray. So you have this cumulative background that is detected that is telling you that you have a very large population of sources out to the largest distances in the universe that are possibly accreting black holes. So this is, again, a nicer version, I think a more visually interesting version of the plot that I showed you earlier for the nearby universe. So this is a famous plot that's called the M-sigma relation, which is the black hole mass on the y-axis and the velocity dispersion of the bulge on the x-axis. And what is shown here in ellipses, it gives you an idea of the error bar in the measurement. So this is the correlation. This is the very famous correlation called M-sigma correlation that was first found by Magorian et al. And later confirmed, plotted in these specific axes by Ferrarese and Merritt. So what you see here, much of my talk is going to be trying to understand how our theoretical models in the framework of structure formation in the universe can give you this kind of correlation and understand what gives you the slope, what gives you the scatter of this correlation. Okay, it turns out that fundamental physics, accretion physics likely, actually dictates the particular slope of this correlation and the scatter. We'll get to that. That's sort of where I would like to end the talk, so let's hope I get there fast. So as I said, there's a lot of evidence for the co-evolution, that's the buzzword actually these days, sort of co-evolution of the galaxy, the stellar component of the galaxy and supermassive black holes in galactic centers. And this is just an illustration to show you that if you do a census of the stars and you do a census of accreting black holes, you find that the shapes are quite similar in the sense that they both peak at the same time, okay, in the universe. So this is redshift, which is time, and you find that roughly between 2 to 3, both of these things kind of peak. And it's not surprising because what makes stars, I mean, you get star formation occurs because of the presence of dense cold gas, and in order to fuel a black hole, you need gas as well. So it's a gas supply, really. What's reflected there is the gas supply of the universe. And in fact, the fact that everything dumps down at lower redshift is that all of the gases, most of the gas in the universe has actually been consumed already at this point. So that's why this is sort of falling off. And we can see that the growth probably occurs in tandem. So the other interesting thing I told you is this is all in the context of the merging hierarchy of cold dark matter models. Then the question is, if galaxies merge, the stellar component merges, then the black holes have to merge. So what's the evidence for merging black holes? As I said, the holy grail is really to find the gravitational waves that you get from sort of the dying gasp of a merging black hole. But the question is, en route to merger, do you actually see these black holes? And it turns out that we are finding a handful of pre-merger binary black holes. So this is a very famous image from the Chandra satellite of NGC 6240, and you see these two bright nuclei, which are two accreting black holes sitting in the center of a galaxy NGC 6240. It turns out, this, as you can see, it's a pretty messed up galaxy. This galaxy is actually merged fairly recently. When I say things like recently, I really mean in cosmic time, right? So kind of a gigayear or two. It's merged in a gigayear or two, and so you have these two surviving black holes that are both actively accreting because this is a gas-rich environment, and you're detecting them as a pair. So there have also been detections in the radio, and there are several groups, particularly there's an active group in Germany led by Stephanie Comosa that is finding, that's been focused on finding more and more of these candidates. So in order to give you a flavor for how much this field has moved since even 10, 11 years, I want to show you, this was the kind of work that I did in my thesis. So, this was sort of the prize plot from my thesis. And and of course, we lost the boat actually in this paper. So we sort of found this correlation, but because we were so focused theoretically and not in terms of the observed properties of galaxies, we were focused on dark matter halos. So we predicted a correlation in the properties of the dark matter halo that is hosting the black hole rather than the galaxy that's hosting the black hole. We could have been really famous if we had actually noticed that and had sort of not worn our theoretical hats. But anyway, we predicted that the black hole mass should be somewhat correlated to the properties of the halo. And I think what is important to note here is sort of this exponent. And this is going to come back to other aspects when I talk about self-regulated growth of black holes. So this is, we thought, was about 5. So what we were able to predict then was, from the sort of globally averaged approach, was sort of potential accretion histories for black holes. So this is over time. So here, we could have an accretion history where you have starting at pretty high rates, falling off, then becoming very radiatively inefficient. Or you could have modes where you don't become super inefficient, but you do still become inefficient. So early on in the universe, you're accreting quite rapidly. You're probably a quasar, and then you become this little wimpy thing you find in the center of the Milky Way. So these were sort of the models that we had predicted. And you'll see, I'll show you some results of the much more powerful stuff that we can do now. So what do we do now? So we now include explicitly, as I said, a model for galaxy mergers. And we make a few simple assumptions that are suggestive from empirical data. Okay, so we assume that you have two galaxies that merge, and the fixed fraction of the available cold gas gets funneled to the center to power the black holes, and it can be accreted at arbitrarily high accretion rates to grow the black hole, because the goal here is to start with small seeds, grow them to about 10 to the 9 solar masses by redshift 6 or so, 2 gigayears after the Big Bang, to power the quasars, and then somehow figure out how to shut them off at later times to explain the populations that you see nearby. So what we find, the approach that has been followed is that, as I said, some of the assumptions are that the amount of cold gas is really what sets the accretion history in a way. And that is controlled by what fraction of it is accreted, we think translates into this efficiency factor for the accretion process. So you assume a simple light curve for a quasar, and we can assume whether it's dependent or independent of luminosity, whether the lifetime is. And so what we find is the growth is dominated at early times by accretion and at late times by mergers. So for example, if you look at the black hole at the center of Virgo in M87, so from redshift 1.5 to today, it's not grown by accretion. Okay, there's not a whole lot of gas there. It's actually grown mostly by mergers from about redshift 2 to today. But prior to that, much of the growth, so that's a supermassive black hole, a few billion solar masses in our neighborhood, and we think that at redshifts above 2, this hole actually grew mostly by accretion. So that's sort of the picture that is emerging. And I just want to point out, there are a lot of people who've worked in trying to develop these models. So as I said, the first challenge in trying to explain the observations is the seeds. And so this is a famous diagram from my advisor, who's very well known for making these little squiggly diagrams that capture quite a lot of physics. So what is shown here are the various pathways to making black hole seeds in the universe. And I want to focus, so the new model that we have is a variation in one of these sort of strands, which is you have direct collapse, formation from direct collapse of pre-galactic disks. So that's sort of the channel that we have recently pursued. So before outlining our results and our model, giving you a feel for our model, let me tell you what the conventional wisdom was till about 5 years ago. So people assumed that you form black holes from the remnants of the first stars that form in the universe. They are referred to as population 3. So this is when the gas that formed the stars was virtually metal-free. And so you form these stars that then burn out and leave you black hole remnants with solar, the masses of these stars, it's not clear what those final masses are. We think they're quite massive. They're a few hundred solar masses or so. And the final black holes that you get, we think, are of the order of a few hundred solar masses. So it turns out that this sort of seed mass poses challenges for explaining the redshift 6 accreting quasar population. So what you really need are more massive seeds and new ways to make more massive seeds. So essentially you need seeds that are of the order of 1,000 to 1,000,000 solar masses to form naturally in a sort of feasible way in the very, very early universe. So these ideas were pursued early on. The idea here is to try and exploit viscous transport. So you have these very large pre-galactic massive accretion disks which transfer angular momentum out, siphon the gas in, push the gas in, and end up forming a central massive object. So there's some kind of runaway or post-Newtonian instability, and you form a seed black hole in the center of these disks. So it turns out, obviously, as you can see right away, what is key to this question and understanding the feasibility of this method is whether this accretion disk, this pre-galactic accretion disk, is stable itself to global instabilities that will cause fragmentation, that will prevent the gas from flowing into the center and actually form stars, right? So you need to understand the dynamical stability of these pre-galactic disks, and that is precisely what we did with my postdoc Giuseppe Laudato, where we did a proper dynamical treatment of the stability of these very, very early pre-galactic disks in the universe, and try and figure out what are the conditions under which this disk will actually funnel matter to the center to form a seed versus fragment. So of course it turns out that there are particular regimes of interest that give you the various outcomes. And so there's another model here that I should mention that Mitch Bagelman and Marta Voluntari have been pushing in recent years, which is an alternative sort of to what I'm going to talk to you about. It's not entirely an alternative. It's very similar in the sense that they focus much more on the final stages of this coalesced massive gas seeds. And these objects are referred to, you might have heard of them as quasi-stars. Okay, so what's the model? The idea is very, very simple. So you have a dark matter halo, and the baryons inside the dark matter halo settle, collapse, and form a nice exponential rotating disk. And I'm stressing the word pre-galactic here to emphasize that this is not enriched with metals, so cooling is not as efficient, and cooling is only through atomic or molecular hydrogen. And so what you end up having is you drive some instabilities. The disk becomes gravitationally unstable, so you have non-axisymmetric instabilities like bars and so on that funnel angular momentum out, move mass in, and you form a central black hole. So as I said, the key is try to understand the various conditions under which you would actually form these seed objects. So it's a brief outline of the sort of sequence of events that we think occurs, that we've now tested with simulations, and I'll show you some of those results in a bit. So you start out with a dark matter halo mass with some mass m, virial temperature, no metals, as I said, and depending on the coolant that's available, if you have just molecular hydrogen or atomic hydrogen, you could cool this disk down to about 4,000 Kelvin or a few hundred Kelvin. Now, if the virial temperature is in excess of the gas temperature, this gas will collapse. It will form a rotationally supported disk. And this disk will be subjected to the usual sort of Toomre instabilities. And we can then examine at the onset of instabilities, follow it in time, and see what the fate of this disk is. So it turns out that the disk evolution for this pre-galactic disk is essentially a tussle between accretion and fragmentation. And because you form these bars, you form these non-axisymmetric structures that very efficiently transfer angular momentum, you can redistribute angular momentum, feed matter to the center, and you can form a central mass, which actually then stabilizes the disk a little bit. So what is very, very interesting for me, one of the exciting things about this model is that the accumulated central mass, therefore the black hole mass, seed black hole mass, automatically depends on some of the key properties of the dark matter halo. So it depends on the spin, which tells you the extent of rotational support in the halo and in the baryons, the halo mass, the ratio of the gas to virial temperature. So what is very interesting here is in the population 3 case, you may remember that you have a star that ends up. There is no correlation initially between the properties of the gas, the surroundings, with that of the seed black hole that you have. Whereas in this model, you are automatically starting out with some initial correlation between the properties of the large-scale environment of the seed and the seed mass itself. And this is very interesting because we want to understand where the correlations that we see today arise from. Do they arise from the initial conditions, or are they a consequence of just the merging hierarchy in CDM? So it's very, very important to have an alternative model where you have some initial correlations which you can then propagate over time and see whether that's really what explains. I mean, I'll skip this view graph. I mean, it's just a little more details, and if anyone wants more details, I'd be happy to talk to them. The only thing to note here is this equation, which is we predict the mass function, so the spectrum as a function of mass, the abundance of black hole seeds that you could get as a function of redshift, which is just a function of the parameters, and one of the key parameters, this lambda, is a spin parameter. It's a measure of the rotational support for the gas. And it turns out for cold dark matter models, we actually know what the distribution of lambda is in dark matter halos. Because we don't have a theory to ab initio to understand what the relationship between the dark matter and baryons is vis-a-vis their angular momentum properties, we assume that the gas has the same angular momentum properties as the dark matter. So key to the mass function that you produce for the seeds, one of the key parameters is this distribution of spins. So what are the criteria? As I said, there are 3 different possibilities when you look at these pre-galactic disks and their stability, and you find that there are 3 interesting regimes. In one regime, the disk is extremely unstable. It fragments, forms stars, and there's no central mass concentration that's formed. So you don't form seeds. In the second regime, you form stars as well as seeds. So you have to consistently follow that and see, for a population, as I said, of objects that we're going to be looking at, we're going to have to follow all these possible outcomes and generate the whole population to see what the seed mass function is. And of course, the most interesting regime is this one, when the disk itself is quite stable, it doesn't fragment, and it accretes gas into the center to form these seeds. I'll kind of skip this quickly and tell you that the 2 key parameters are the threshold, the onset of this instability, the dynamical instability, the Toomre Q criterion, and of course the cooling criterion, right, of what actually the coolant is. So you have to do the physics of either atomic or molecular cooling and calculate what the cooling time is compared to the viscous time of this disk. So that's what sets the importance of either process. Okay, so this is our final prediction for the mass function. So this is the abundance of seeds as a function of black hole mass. This is at redshift 15, which is very, very early in the universe. We have no observations at this epoch at the moment. And so what we have predicted here are for various cases that I talked about, the cases with and without fragmentation. We can show that the mass function, notice here, peaks at 10 to the 5 solar masses. So we've now succeeded in making very massive seeds. So we've now pushed out, we can now make a few rare 10 to the 6 solar mass seeds as well at these very, very early epochs. Once you've been able to make seeds that are of the order of few times 10 to the 5 solar masses, then explaining the population of quasars at redshift 6 is not a problem at all, because then you only have to grow by a few orders of magnitude within 2 gigayears. You need to grow the seed black holes from 10 to the 5, 10 to the 6 solar masses to about 10 to the 9 solar masses within 2 gigayears. And that is very, very feasible. So once again, I want you to just take a look at this equation and note that there are a couple of key parameters. It's sort of a very simple it's a very simple idea. It's quite elegant, and what's interesting is that you see here correlations between the properties of the black hole and the mass of the dark matter halo in which these seeds are forming. So this is a model in which you have an initial correlation between the mass of the seed black hole and the dark matter halo itself. So what this shows you here are 3 different models with varying degrees of efficiency of forming seeds and how the seeds actually grow with accretion. So this is the initial seed at redshift 15. This is at redshift 12. So notice that you are accreting and you are growing in mass quite rapidly. And these are for the 3 different sort of exploration of parameter space. So another thing to point out in these models is not every dark matter halo in the universe is initially seeded. So not every galaxy at very, very early times is going to have a seed black hole. Some of them won't. But eventually, pretty much every galaxy will get a black hole because of merging. It'll merge with another one that has a black hole that would then sink to the center. So the probability, it's very interesting and important to note as a function of time, what is the probability of hosting a black hole seed of any given mass, and that's something we can explicitly calculate. Okay, so what are the tests of our model? So let me quickly show you these 2 sets of simulations where we've managed, so this is sort of work from my group, very recent work that's just submitted to Nature. And this is results from another group in Cambridge, England, where we've looked at primordial gas. So this is unenriched gas. So this is the formation of the first objects in the universe. And what you find, you follow at very high resolution the fate of the gas. So what you see here, these blobs are actually the gas, and the darker stuff here are the sort of central massive. So we are going down. This is an adaptive mesh. So we are going down. We are zooming in and zooming in. So in fact, here we're looking at 1 parsec. Okay, we are resolving 1 parsec. We are starting from about 1.5 kiloparsec to 45 to 15 kiloparsecs, and we are zooming down all the way to 1 parsec. So this work, this kind of work has been done following the formation of the first star, and what we have done here is slightly more challenging because we are looking at regions that have a varying amount of angular momentum. So when people have studied the formation of the first star, they've always looked at the first region in the universe that collapses, and they zoom in there and they follow it. Okay? But what we wanted to do, because we are looking at correlations with spin, different regions in the universe have different spin parameters, so we are focusing on different halos, which are not necessarily the halos that will collapse first, because if there's a lot more rotational energy, you need more time to get rid of the rotational energy before the gas can collapse. So these are very, very challenging simulations. At the moment, there are only these 2 sets available. So what I wanted to show you here are the 2 different fates that I talked to you about. One in which you have some fragmentation, so you have a central object and some fragmentation happening as well. And this is another case where you actually have a central massive object. That little blob is the central massive, that's the putative seed. The gas is accumulating at very, very high density in these very, very small regions of a parsec or so. And so we think that sort of this, this model, sort of the predictions of this model are upheld by simulations. As I said, there's no observational data at those epochs in the universe quite yet. Okay, to give you a feel for what we actually do, how do we run these models? So the method, I should point out, was pioneered about 6-7 years ago by Marta Voluntari in her PhD thesis, where they came up with this scheme of doing Monte Carlo realizations of generating sort of merger histories in cold dark matter models. So you start with a galaxy today, and you work back its antecedents and you find the merger history, so all the dark matter halos. And what is shown here figuratively are black holes as these little black dots in the centers of these halos. So what you find if you follow all the way back to very, very early times in the universe, notice that there's a seed here, there's no seed in this one, they merge, and the merged object ends up with a black hole in its center. Then you merge with another object that doesn't have a seed, and you still have this seed. So the black hole grows. With every merger, there's an accretion episode that is triggered, and the black hole grows. So you can generate these trees, the merging hierarchy trees for cold dark matter models, and then you can start seeding them at high redshift and following the fate of these seeds, and that's sort of what we do. And what we have done is then investigate these 2 sets of seeds. So one are these sort of population 3, the remnants of the first stars. That model is this, where basically this is the mass of the black hole. So basically, you don't have a very, very sharp distribution. Basically, you have most of them at about a few hundred-ish solar masses. And then, sorry, that's this model, a few hundred-ish solar masses. And this is our seeding model, where there's a range going all the way up to 10 to the 6 solar masses. So we seed the initial dark matter halos with seeds drawn from these two distributions, and then propagate them down and look at the distribution of properties for the population. So I just want to point out a couple of, oh gosh, okay. I just want to point out a couple of interesting things about mergers, that the mergers are very rare events, and they require the merger of two galaxies with a central black hole, and not every merger is going to produce a growth episode for black holes. So only a fraction of them, about half of them at any given time, will actually trigger an accretion growth episode. So anyway, let me quickly move on to show you what our results are, and then I want to make sure that I show you a couple of movies of the actual mergers, predictions for the mergers of black holes. So what we find is that when you start out with an initial correlation, that is these models, versus you don't start out with an initial correlation, the point is to see in the far future today, so what you see here are data points from the M-sigma relation that I showed you earlier, with the error bars, so that's data, and overplotted are the results of our model. So you find already that in all these models, there's a very, very interesting feature that distinguishes it from this model, which is you are not seeing very, very low mass black holes. So there's a paucity at the low mass end of the black hole mass function. Both models can very adequately reproduce the high mass end of the black hole mass function. This is the observed black hole mass function today, the M-sigma relation. So notice that the existence, and you are propagating both these seeds through the same merging hierarchy in cold dark matter models, right? And so what you find is the key difference that tells you the difference between the seeding models that has a signature of the seeding model is the low mass end. And of course, the low mass end is very, very challenging observationally. So this is again on a different plot where the two models are overplotted in blue and red respectively. So this is, the prediction for this correlation at earlier times than today. So redshift 4, redshift 3, and redshift 1. So we find that you can discriminate these models by looking at the low mass end of the black hole mass function, and the prediction is that the seeding is reflected in the amount of scatter you will have in the low mass end. So if you have a lot of scatter, that tells you that there are many channels to make seeds. Okay, so now we have a very good understanding, we think, of the stages in the growth of a supermassive black hole. So I'm going to start talking a little louder, faster, not louder. But so you have a merger, very messy merger, and we think that drives a lot of gas to the center. The luminosity of the accreting, so there's a merger of these two black holes. They start accreting gas, they glow, and you will see them as a quasar. And there's a stage intermediate to that and post this stage where we think there's a lot of dust and obscuration, and you will not see this object as a bright luminous quasar. You will see that as a very obscured object that's probably re-radiating in the infrared and not optically luminous. So we think that we understand much better the life stages of quasars. So as I said, one of the other key important discriminants for the seeding models are the merger rates. So LISA, this proposed satellite that should measure the black hole coalescence, gravitational waves from black hole coalescence, should be able to discriminate between these models with the current specs. So one key piece of physics that is needed in addition, which I mentioned in our model, is a self-regulation for black hole growth, which is black holes appear to cap their own growth at some point. They reach a certain mass, and at every epoch in the universe, they seem to cap their own growth. And it appears that this is a very important key feature, and this is a new result that we've just submitted as well. We think out to the highest redshift, this is data with error bars. We think that even out to the highest redshifts, we have evidence for self-regulation and the existence of a correlation. So I'll skip some of this, which is my own work, and I want to show you this, which is how else do you ratify this picture? So you want to understand what is really happening when galaxies merge and their central black holes merge. So the idea is the detection with LISA, you will not be able to localize where the gravitational wave burst is coming from, so you need some other electromagnetic counterparts. You need some other signature in the electromagnetic spectrum, either in the UV, IR, or X-ray. And initially, we think that in the process of merging itself, we think that stellar dynamics can grind the black holes to the center initially, but then after a certain point, there's a hang-up. It's called the last parsec problem, famously. And we now think, me and one of my collaborators, Phil Armitage, have worked on this extensively, that the presence of gas in the centers of nuclei could actually drive the black holes into coalescence much more rapidly than was thought before. And the signature of such a process are, you can make very precise predictions for what kind of electromagnetic counterparts you should see. Because there's a lot of gas, you should be able to see a lot of electromagnetic counterparts. So let me quickly show you a movie. And before that, I'll show you what the process is. So the process that is going to be modeled here, the simulation, is you have an accretion disk, a fairly massive accretion disk, lots of gas in the center of a galaxy, which is seen now. You have a central primary black hole, and you have a secondary that falls into that disk. And the question is, how long does it take for that secondary to spiral into the center? And it turns out that the presence of this gas disk, where the gas mass is comparable to the mass of the secondary, drives it in very, very rapidly. And it's very similar to a problem in planetary migration. It's called type 2 migration, which is aided by the presence of viscous talks. So if you look at the sideways of the accretion disk, you find that the secondary, so the primary is here, the secondary is here. The secondary actually opens up a gap in the accretion disk, starts migrating inward because of unbalanced viscous torques. And what you find is this mass of the accretion disk, which is inside where the secondary is, has nowhere to go but to fall in, and gets very, very rapidly accreted as the secondary falls in. So you could have a precursor. Prior to the gravitational waves coming out of this merger, you could have some of this gas glow in the X-ray, and you could even have post-cursors depending on how much gas is left over and the distribution of that gas once the holes have merged. So let me show you the case. So there's a critical radius at which gravitational wave torques due to gravitational waves take over, and you don't have to worry about the gas. But the point is to get the gas from about a few parsecs down to this radius, where gravitational torques will then rapidly take you in. And what was really unknown was these viscous torques. What kind of time scales are really, really needed to, if it's comparable to the age of the universe, then this process is not clever, it's not efficient, it's not feasible, because then you wouldn't be able to merge them, and you're not seeing enough binaries with large separations to account for this. So we are clearly merging black holes quite efficiently, and we need to understand how that happens. And we think that this is a movie that we made from our simulation. This is a head-on view of the accretion disk. The primary is somewhere here. The secondary is going to be dropped in the disk, and what you'll see the sort of spiral density waves being generated. The movie is moving. You'll start seeing it now. You'll see the spiral density waves, and you'll see the secondary starting to plunge in. And what is shown here is the surface mass density of the accretion disk and how that changes. Notice the gap has now been opened. There's a gap that's opening, and the secondary will start moving in. You start piling gas to the center, and the outer accretion disk actually decouples pretty much from the inner accretion disk. So at this point, notice the fate of this gas, the gas that is sitting here in these inner regions on coalescence, is going to actually give you an electromagnetic precursor.
What is the ratio of the primary versus secondary?
In this particular one, the mass ratio was 1:10. And we've done this for several cases. And it turns out, of course, for the more extreme mass ratio cases, this is a very, very efficient process. Because as I said, the amount of gas that you need is comparable to the mass of the secondary. So, the equal mass case is probably not going to be driven quite like this. It's slightly different. Because you'll need to pile a lot of mass there if it's equal mass in the disk. And then the disk will become unstable. So I can't really follow this kind of evolution for that. So what's interesting, as I said, there's a lot of gas in the center that gets piled up that's going to give you probably some kind of prompt signature and an afterglow. And let me quickly show you one more movie before I stop, which is, what other signature could you possibly have aside from for implicating the role of gas in affecting these mergers? So it turns out that, in the first case that I showed you, they were on a circular orbit around each other. So the question is, if the orbit is somewhat eccentric, which is probably the more natural event during a merger, because during a merger it's quite violent, you can have a merger along a lot of different axes, so you probably end up with a nicely eccentric binaries to start with. And the question here, it's more complicated and it's interesting. The reason why the eccentricity is interesting is in the gas-driven phase, the eccentricity will grow exponentially. It will grow very, very fast. But once gravitational wave torques take over, it gets exponentially damped, actually. And it turns out that LISA is going to be very, very sensitive to the measurement of any eccentricity at the point of merger. So 1 week before the merger, it's going to be very, very sensitive to even eccentricities of the order of 10 to the minus 5, 10 to the minus 6. So the question is, if eccentric binaries are really the norm, then what is the rough order of magnitude of eccentricity that survives at later times? So this is a movie that shows you, it's pretty much, it looks very, very similar. So it turns out that the eccentricity does not change the time scales that affect the merger by the gas in the initial stages. However, what it does do is it provides you another unique signature that LISA can actually pick up, which is the residual eccentricity at the end of about 1 week from the merger. So you have an eccentricity that is finite, and this is for the case of a 10 to the 6 solar masses, and 1 week before the merger, you find that there's a finite eccentricity, and that is actually measurable. And this effect is stronger for extreme mass ratios, and I just want to point out before I stop that, for LISA, the bulk of the events are going to be MREs, the sort of extreme mass ratio, just given its sensitivity and so on. So, so I want to just end with the idea that there will be many interesting electromagnetic counterpart signaling binary black hole mergers, which will be a test of this paradigm. And of course, the exact environment of the merger will dictate. There's a lot of uncertainty because we don't know the gas densities in these environments, so we don't know exactly which physical process is going to be dominant. But we have a real good understanding of the various possibilities. So I'll just stop here with what I think are some of the exciting future prospects. So I think, instruments like the LSST, which will be doing sort of detailed time studies, and LISA will revolutionize this field because we'll be able to constrain these models much more tightly. And we'll have very large samples. We'll be able to go down further in the luminosity function to the faintest sources so that we have a much better understanding of the entire population of black holes at early epochs and today. So I think, I hope I've given you a flavor for how you can do some big picture models where you can look at the accretion history of a population, as well as looking at some important microphysics that's part of the accretion that's important. So especially for the students, I wanted to give you a flavor of the work, how it's a combination of very interesting accretion physics that you then use to build a bigger picture in the context of structure formation in the universe. I'll just stop here and take questions. Thank you.
Thank you very much, Professor Natarajan. A couple of questions. Bhaskaran.
I don't understand the model and other things, but you said there is this dark matter halo.
Yeah.
So that also will be sucked in.
No, actually, so that's a very, very good question. So the dark matter halo, it turns out in the centers of galactic nuclei, the density of dark matter is too low for the accretion rate. So if I calculate, so what you want to calculate, right? This is a question actually that I'm asked quite often. So you want the accretion rate of baryons over the accretion rate of dark matter at the centers. So, very, very small radii, so 1 parsec or so. And it turns out that this is very, the dark matter accretion rate is really, really low because the density profiles that we think that most of these bright galaxies that have the massive black holes, it turns out that the baryons appear to dominate in the center. So this is the dark matter, and these are the baryons. So we think that the baryons actually are lumped up in the center. So this is not drawn to scale, okay? So this is few parsecs or so. And this is further out. And once you reach outside the innermost parts, the dark matter dominates at every radius, pretty much. But in the inner region, if you actually calculate explicitly, so you can calculate this for something like M87, and you find that this ratio is like 10 to the minus 10 or so. So the accumulated dark matter mass that is going into the black hole is really tiny. It's not, it's not relevant for the mass budget.
So black hole is bright inside.
I wouldn't say it's bright inside. It's baryonic is all I can say. Well, it's baryonic matter that has made it in. Yeah, baryonic matter has made it in.
In the beginning of your talk, you mentioned about doubling time, which is pretty short, 10 to the power 7
Yeah.
or something. I would imagine that that's the case, then something that started a billion years from the Big Bang should disappear by now, right?
Why will it disappear? It'll keep doubling. It'll become extremely
right.
massive.
Yeah. So
Yeah, but it still can't become. It's a good question. So with just
the
this,
size, I mean, what you're talking about.
Pardon?
You start with the seed of one solar mass, let's say, no?
Yeah.
You can calculate how big it could be before it swallows the whole thing. Because you have some finite object to swallow, right?
No, I'm not quite understanding what you're saying. So the thing is, if you start with a mass, that's the doubling time of that mass,
No,
right?
But the evolution.
So,
You
right.
start with the gas and then density perturbation, there's clumping of
No,
matter.
that mass doubling time is
Yeah.
the mass doubling for a black hole
Yeah, I
that's
understand the
accreting,
point.
right?
Okay.
Not for the density perturbations. The density
No,
perturbations are in the dark
no,
matter.
I understand the point. That's
Yeah.
not what I'm saying. After the black hole started here,
Started growing in a
yeah,
galactic
right.
center.
So
Yeah.
how much of matter has got to swallow? What do you mean?
The gas has to reach the center and feed the hole, yes.
Right. You can estimate the thing, right?
Yeah. I mean, so that's what, you find that you cannot grow it from 100 solar masses to 10 to the 9 solar masses within 2 gigayears, which is redshift 6, without exceeding the Eddington limit. So that's the crux here.
Oh, I see, okay.
That if you don't want to exceed the Eddington limit, then you can't grow it.
Yeah. Second question, the seeding business here, see if you have stars at different distance from the center here, black holes may be formed at different points.
Oh yeah, sure.
Yeah. So I don't understand your seeding business here. Does it always
No, the
start from
seeding
center?
business will happen in the center pretty
Only in
much.
The center, why not at the other points?
No, because the density is highest in the center. So that's where the seed will form. As for the fragmentation, so remember in the cases where you form a central seed and you have fragmentation around, and if those things form stars and there's a stellar remnant, then you will have remnant black holes, stellar mass or whatever, that will start spiraling into the center. But the seed itself, these massive seeds that are forming from the direct collapse of these gas disks, they will form in the center because the density criteria are not satisfied anywhere else in the disk. It's an exponential disk, so the density is high enough only in the center.
No further questions. Let us thank Professor Natarajan for a wonderful lecture. We move on to our next speaker,